Thanks everyone for coming to this session on the very last day. I'm delighted to be back at CGSI. This is honestly one of my favorite meetings of the year, and I go to a lot of meetings every year. So thanks for inviting me back. My name is Iman Hajirasouliha. I'm an associate professor of computational genomics in computational biomedicine at Weill Cornell Medicine in New York City. And my lab is a pure computational lab, but we do a lot of different projects. It's like a very diverse set of projects. In fact, I started in 2016, around the same time CGSI started, and I did say this last year too. Sort of like my interest kind of shifted to more like AI and machine learning in healthcare, similar to like what CGSI is now focused on more. And today, I'm going to talk about some of the stories about AI in fertility and women's health. So it's probably like a new topic for some of you guys. So I'm gonna introduce some of the challenges in this field. But we do have a lot of other projects in pathology, genomics, applications to cancer, and so on. So I'm happy to talk about, discuss this offline as well. So infertility affects like 1 in 6 couples. So it's a problem. And these days, a lot of patients, increasingly utilize IVF or assisted technologies to essentially conceive. So in the last 40 years, since people started using IVF, we have now about like more than 8 million IVF babies. So it's growing very fast. However, the cost of IVF or in vitro fertilization is still very high, and the success rate is pretty low, especially when the maternal age advances. Women over 40, for example, have like a very small chance of having successful IVF. So therefore, often, people do several cycles, and that can lead to multiple pregnancies or, other complications, like health complications. So in 2020, me and a colleague of mine wrote this review article, sort of like discussing ideas of how to use precision medicine and AI to optimize some of the tasks in an IVF clinic. Especially, we were focused mostly on optimizing embryo selection because many clinics use imaging techniques, so you have like images of embryos. Sometimes you can also do like genetic testing, so you can also use sequencing data or like genetics data. But there are a lot of other tasks as well. So you can analyze eggs or sperms individually, or you can do like smarter monitoring of fetal heart after the transfer, or eventually like the whole process can be more like automated, and you can use AI to like optimize some of the process. In fact, IVF is like a very complex process. There are like many steps. It starts with ovarian stimulation, and actually this is like a figure from a review article just came out a couple months ago by colleagues in Imperial College London. And you can see actually even they don't really discuss pre-treatment counseling and diagnosis, but it's still if you want to do like IVF, there are a lot of steps. And in the last, I would say 3-4 years, it's not very long, people have started looking at these steps and trying to use like machine learning, AI to optimize some of these steps. For example, starting with ovarian stimulation, you can predict the dosage of the hormones you are giving to patients. You can, for example, predict the optimized day of trigger when you do the trigger shots. You can assess oocyte or sperm. You can look at embryo images. You can assess embryos. You can do look at the ploidy status of embryos. And this is in fact like what is the focus of my lab, sort of like looking at embryo assessment. You can do like embryo selection and so on. So there are a lot of steps, and AI can be actually utilized for these steps. And people started looking at these problems. So there are increasing number of research and papers from a newly formed community. So how do we do embryo assessment? Traditionally, there's a team of embryologists. They look at the morphology of embryos, typically at day 3 or more likely at day 5. So they, they are experienced embryologists, so they look at the blastocysts, and they look at different features of the blastocysts. So for example, there are different grading systems. You can see how well expanded the embryo is. So expansion has a score. You can look at the inner cell mass. You can see the quality of the trophectoderm. So essentially, they have different, like a grading system. It's a manual grading. And as you can guess, this is very subjective. Different clinics have different grading systems. However, this is relatively inexpensive. It's non-invasive. They just look at the microscopy images, so it's pretty inexpensive. So these are some of the examples of these grading systems. One of them is the Gardner system. So again, as I told you, there are like different values for each of these components. So you can say, oh, there's a 4AA embryo, that's a good embryo, but it can be, like a 3BC embryo, that's like a bad embryo. And as you can see, there are a lot of different combinations of all these, numbers and grades, not very standard. So in fact, like we looked at, more than 10,000 examples in our clinic, and the scores are, like there are like hundreds of different categories of these scores. And in fact, like in our clinic, sometimes they put like minus and plus because they are not sure, like between like an A or a B. So they do like A minus, for example. So they even like add to the complexity. There was a recent paper from some of our collaborators. They tried to simplify this grading a little bit. So instead of using this more like complex score or grade, they map it to like a numerical score. So they essentially add, like the values of ICM, trophectoderm expansion, plus a biopsy day, because that's also like some interesting feature. And they say, okay, like if it's you get a value between 3 to 14, and it's a good embryo, it's like maybe less than 5. Fair embryo between 6 to 9, poor embryo up to 14. So you can simplify a little bit. And then they showed in a paper that this would correlate well with an outcome such as fetal heart. In some clinics, including Wildcard medicine, there are machines they are called embryoscopes. These are time-lapse photography machines. So essentially, like from day 0 to day 5 or 6 at the blastocyst stage, every 10 to 15 minutes, you can actually get an image of the embryo. So you can actually look at the development of the embryo as well. And some clinics utilize these like time-lapse images for better assessment of embryos as well. Again, like this is non-invasive, obviously, similar to just a regular microscopy imaging technique, but the machines are very expensive, and it's still, like there is like some debate in the community if they are useful or not. Another method for embryo selection is this pre-implantation genetic testing. These are invasive. It's not very invasive, but still, like you have to take out the embryo. You have to do like a trophectoderm biopsy. So you wouldn't touch the actual inner cell mass, but you can take out like a few cells from outside the embryo, do sequencing, and see if there are, like abnormalities in the chromosomes of the embryo. So you can do, for example, next generation sequencing. You can detect, if say there's a Down syndrome, if there are extra chromosomes and things like that. So you can essentially, with high accuracy, distinguish between euploid embryos and aneuploid embryos. So how we can utilize AI to essentially increase the success rate and optimize some of these steps in the IVF clinic. And in fact, we have a lot of data sets now because, people use IVF a lot. So we have part of the standard care at Weill Cornell. We do these time-lapse images of embryos. We do have a lot of sequencing data because a lot of patients do pre-implantation genetic testing. So we can essentially train models, AI models, to do classification or these prediction tasks. So a few years ago, my colleagues and I studied, if a deep learning model can actually do embryo assessment. So this was really the first paper in this domain of using AI for embryo assessment in human embryo. And we had a large data set because, we have a very large clinic. So almost 5,000 cycles a year is done in our clinic. So what we did was basically like a supervised model. So we use convolutional neural network to look at these images, essentially. So the labels come from expert embryologists, and we just ask them to do good versus poor labels. So it's like a binary classification, if an embryo is good or if an embryo is poor. And we wanted to see if, CNN can actually do this classification task. So we obtained more than 10,000 embryo at the time. We used, so the embryologists gave us 3 different categories when we asked them. Good embryos, poor embryos, and a category was labeled as fair embryos because they didn't have really a consensus of these fair embryos. They were sort of hard to assess, I guess. So we sort of used, the good embryos and fair and poor embryos to train our neural network. So we used 6,000 images, examples from good embryos, 6,000 examples from poor embryos, and we trained this neural network, and then we did some tests on independent held out test set from Weill Cornell, and as you can see, our accuracy is actually very high. So we can, with 97% accuracy, we can find, good embryos versus poor embryos. This was very encouraging. And we also decided to sort of apply the same model to data from clinics from outside the United States or our center. So the images are a bit different because some of these clinics use different protocols in IVF. But again, with more than 70% accuracy, we could distinguish these embryos. And this is only looking at images of embryos. So these are some of the AUC curves for these models. As you can see, especially for the Weill Cornell test data set, the AUC is very high. And at the time, we used the Inception version 1 model. But we did a lot of testing of different convolutional neural networks. Just a quick note here. I mentioned there was a fair quality group too. So we asked Stork, our algorithm, to classify those as well. And the end result was pretty promising because the ones that Stork predicted as good when we did the retrospective study, they had a higher likelihood of live birth. So that's also interesting because embryologists couldn't really figure out which one was good, which one was poor. We also developed this user-friendly user interface. So embryologists can essentially easily upload images of embryo to a cloud-based system, and they can get the classification result of the method. So I mentioned ploidy status is a critical step in assessing embryos. We also wanted to see if we can actually predict this ploidy status using an deep learning image-based model. And this is a pretty challenging task. And we actually concluded that image alone is not enough to predict ploidy. So we studied images together with additional clinical factors, and also together with like morphokinetics, because we had access to these time-lapse images of embryos. So we published this paper early last year. This was work of my student. He's actually graduated now, Joshua Barnes, published in Lancet Digital Health. We looked at like additional deep learning models to predict the ploidy status of embryos non-invasively. So this is again the data set we use. We use here more than 10,000 embryos, but we had the PGTA results. So we use the PGTA result as labels. 4,400 euploid embryos in this data set, 5,900 aneuploid examples in this data. But also we had some further distinction between simple aneuploidy, when only there's one type of aneuploidy on one chromosome, and complex aneuploidy, when there are multiple different aneuploidies on 2 or more chromosomes. So this is the model design. We extracted one image at 110 hours, and that's the time point that embryologists use usually to grade embryos at 110 hours. And then we extracted features from those images using a convolutional neural network. But then we added all these additional clinical values, especially age. The maternal age is very predictive in these models. So we added that maternal age, but we also added the score that the embryologist would give, which is also very predictive and has a high correlation with ploidy status. And also the morphokinetics, because we had the time-lapse data. So you can actually see the time point between each developmental stage. So in the paper, you can check, there are a lot of different models, a lot of different classification tasks. So I'm highlighting a couple here in this talk, but if you want to see other results, you can obviously check the paper. But here you can see, this is a result on 3 different independent test data sets. The green one is from Weill Cornell. This is the same cohort. So we had a held out data set from the same cohort that we trained our model on. But the red one is from EmbryoScope Plus. This is a newer machine. So there are some slight differences between EmbryoScope Plus and EmbryoScope. EmbryoScope Plus has more focal points, for example, and it's a newer machine. We also used a data an independent test data from a clinic outside the United States. In this case, we worked with some colleagues in Valencia, in Spain. So you can see, the accuracies are pretty good, around 70% for the task of distinguishing between aneuploid embryos and euploid embryos. If you want to do the complex aneuploidy versus simple aneuploidy or euploid embryos, we even get a slightly higher accuracy. So this is another result that shows on essentially using the complex aneuploidy versus euploid plus simple aneuploidy. So right now we are actually working to extend STORC-A because in the original model we didn't utilize all the time series data and all the different essentially all the time-lapse images. So we are in a new model, we are using the sequence of time-lapse images now. And we also want to generalize the model across different data sets from different clinics. And also we want to fully automate this process, because in the original model, we still had the embryologist input in our model. So we wrote this manuscript recently. This is actually just got accepted in Nature Communications. Hopefully it will be out very soon, but we have a version on bioRxiv. You can check it out. So we use, like a heterogeneous data set. We added some new examples from a clinic in Florida, and these are all now time-lapse images. So we have like videos in our training data set. So we developed this new model, and the idea behind that was we wanted to use the blast score, the score that embryologists would give to embryos, as a proxy for ploidy status. We know that this is not enough to predict ploidy, but we were thinking if we especially add, like additional features such as maternal age, we can do this prediction with a higher accuracy. And again, as I said, we want to use the video. So we mostly focused on images from 96 hours and above. We did a lot of tests, and we sort of concluded that the earlier images were not as predictive as the images from the last day or the last 2 days. So we feed the images from 96 hour to 112 hour in a neural network. Here we use the bidirectional LSTM model to extract essentially features and do prediction of these blast score. And then we have a second component in our model to aggregate the predicted blast score from the LSTM model with the maternal age, because maternal age is, again, like very predictive in these models. So to predict ploidy status. So I'm highlighting some of the results in like here. This figure on the left is the correlation of our predictions for, remember the blast score had like all the values from 3 to 14. That's the score that our embryologists give. And this is on the training data. You can see, our model is actually learning these values very well. There is some, so that when we tested on an independent test data, you can see, still it's not perfect, but still, like the model can, with about like 70% correlation, can actually get these values right. So we have some moderate strength in predicting blast score. So we want to use this blast score that we automatically find in the model to actually predict ploidy. And I'm showing you some of the results. Again, like the paper will come out very soon, but you can also see some of the figures and supplements in the bioarchive version. So you can see, like this is like a bit of a busy slide here, but there are like several different classification tasks. This one here is euploid versus aneuploid using embryoscope data. The second one is euploid versus complex aneuploid, again using embryoscope data, which we trained our model on. The last two columns, we are using embryoscope plus data. So this is, we did not use those examples in our training, but this is like another independent test set from a different machine. And these are all wild cornell data. So as you can see, like the blue bars are when we used a video classification model. So we did not add, so Bella is our model, which uses the blast score that we predict. And as you can see, in all cases, Bella is outperforming a video classification model. So we are very happy with this. And even though, like in some cases, if we use the embryology input, we get a slightly higher performance. For the most part, and in some cases, Bella even outperform what embryologists give us as a score that we incorporate in our model. So these are like pretty encouraging results, and the accuracies are much higher compared to when we only had like a single image. So we have some evidence here that the time-lapse images actually outperform, a single image. And this is something that our embryologists also believe, although like there is still, some debate in the community. Some centers don't really believe in time-lapse, or they don't utilize time-lapse. I'm also highlighting a few other results here. For example, here you can see When we looked at the Spain data and we looked at the feature that the model extracts, and then we did like some PC analysis, you can actually see like there are like the principal components in this. When you look at the Spain data, is actually like very different compared to like North American data, like Florida and New York data. So that's also sort of what we expect, because the Spain data, they have like different protocols. The morphology of the images change. Especially they use some assisted hatching on day 3, so that would change the morphology a little bit. So the feature would be essentially different that the algorithm use. That being said, still, like our model is generalizable to the Spain data. You can see this. We can get again close to 70% accuracy on the Spain data, and that would outperform the video-only model. Again, we developed this user-friendly platform, so embryologists can, enter, like all these fields, maternal age, blast score, everything that was required in the model. But they can also upload images and videos, and they can quickly get the classification results. So this is a summary of Bella, our model. It would streamline the workflow for embryologists because it's completely automatic now. You can, obviously, that will reduce time and effort by embryologists. It cannot, at the moment, replace PGTA completely because we don't get the accuracy to at the PGTA level. But still, for most cases, especially when we are dealing with complex aneuploid embryos, you can do this classification very well. This can also supplement the manual embryo quality grading by embryologists, because now we have an automatic way to predict the scores. And obviously, there is no requirement of embryologists to do this manually. Currently, so embryo grading and ploidy status is one task that is important, obviously. But there are several other tasks in an IVF clinic, including, for example, embryo segmentation. Some embryologists want to segment embryos. Embryo witnessing. Sometimes you want to actually know if 2 embryos are the same or not, if you look only at the images. And there are other predictive tasks as well. So we sort of started looking at this problem of, can we have foundation models, or models that can essentially perform all these tasks at the same time. So we can have a multitask model. And for these, actually, for this foundation model, you heard some talks during the past week. You don't even need labeled data. You can use a lot of unlabeled images. You can create representation of these images and do additional training for supervised training on different downstream tasks at the end. So we trained one of these foundation models on our embryo data. This is a vision transformer, very autoencoder. We actually so this is you can use the unlabeled images, obviously, but we had collected a lot of additional data sets for this project. So we had different versions of our wild cornell data. We had Spain data, but we also added data from Florida and some data sets from Europe. So these are actually public data. The data set from France, the data set from Austria, and some segmentation masks from Canada. And we are still working with some additional collaborators to add to our database. So we are trying to generate to establish this heterogeneous data set. And once we train this foundation model, we can essentially use the foundation model for these downstream tasks. So ploidy prediction is an obvious one, but we can do embryo segmentation, embryo quality assessment, witnessing, and other tasks. And again, we want to make this generalizable to all of these data sets. So far, we trained a model on 18 million images. We call this FEMI. This is unpublished data. It's still work in progress, but I'm showing you some of the results that we already got, and they are actually promising. So they would outperform the state of the art when we compare, like with competing methods. So you can see some results on ploidy detection. In some cases, we actually get to 80% accuracy, which is pretty promising. You can also see, like when we did the quality score prediction, the mean absolute error coming from these foundation models is actually lower compared to competing methods. So again, we want to adopt this to perform additional tasks in future. We are working on different tasks. And also, we are looking at different data sets outside wild kernel to see if they are generalizable to other tasks. I think I would conclude here. So we have now a model that can do multiple clinically relevant tasks. And that model outperforms like all the competing models. And we can use these to essentially implement in different clinics, hopefully soon. I think with this, I would acknowledge people in my lab who work on this project, especially Suraj, a PhD student in the lab who is leading the last two projects. Pega was my postdoc. She is now a faculty in City University of New York. She did implement the original models. And Hosua, another graduate student who did the aneuploidy detection model. And also all the collaborators at Wild Kernel Medicine, the Center for Reproductive Medicine, and collaborators in Florida, Spain, and the UK. And obviously, we are still looking for more collaborations to enhance our data set. Thanks.